Good evening, all. My name is Ganesh Shankar Bhandari, and I am a PMRF PhD research scholar in IIT Roorkee. And I am here to take the live session week 12 for principles for NPTEL course, Principles of Extractive Metallurgy, taught by Professor Tarun Kumar Kundu from IIT Kharagpur. So, like previous week lectures, we will first go with the revision of the previous week lectures. Then, based on the previous week lectures, we will try to solve some MCQ or numerical problems, which will further help you in solving the assignments for this week lectures. Okay, so let's start with the revision of the previous week lectures. So in previous week lectures, we have learned about hydrometallurgy, hydrometallurgical processes for the recovery of um, dissolved metal inside a liquid solutions by with the help of different processes like cementation, electrowinning, gold extraction, and then we will talk about Bayer's process. So there are several methods with the help of which we can recover the metals dissolved inside any liquid medium. Uh, for example, in copper ore leaching, copper recovery from the particular copper ore, we can go with the leaching with the help of H2SO4 acid. Then copper is getting dissolved inside that H2SO4 acid. How to recover that copper from that particular liquid solution of H2SO4? So we can go with the we have read about some processes like electrowinning, electrolysis. So now we will talk about reduction and deposition of metal via electrochemical reduction or cementation process. So cementation process, it's like we can say it is like displacement type of reaction inside any liquid solution. So in this process is higher or we can say less noble metal in the electromotive force series is added to displace the lower metal from solution. So whenever we whenever we are talking about any solution, so it has a capacity. Okay, any solution cannot dissolve metal beyond its capacity. Okay, so it is generally carrying some ionic charge inside that particular metal solution. So what we are trying to do, we are trying to add some extra metal inside that particular leach solution. So what will happen, that whatever the metal we are going to add inside this leaching solution is more reactive than the metal ions present inside that particular solution. So what will happen, this more reactive metal will get leached inside that particular solution and transferring their ionic charge to the other metal which is in the dissolved form inside that liquid solution. So according to the mass balance phenomena, what will happen, whatever the electrons is getting transferred due to the dissolution of metal into that particular liquid solution, they these electron will get transferred to the ionic uh, the metal present in the ionic form in the leach solution. So what will happen, it is that second metal is going to get precipitated in that particular from that particular solution. So for example, when metallic iron is added to a copper sulfate solution, so we have a copper sulfate solution and we are going to add some metallic iron inside that copper sulfate solution. So what will happen, metallic copper will get precipitates and iron goes into the solution. So reaction will be like Cu2 plus, that is in the ionic form in aqueous form in the aqueous solution. Then we are going to add the Fe. So what will happen, this Fe is going to get reduced by transferring their electrons to the copper. So copper will get oxidized and it will get converted into the copper solid, while iron will remain as the ionic form in the liquid solution. In a similar fashion, copper can displace silver from a solution of silver nitrate, or zinc can displace cadmium from cadmium sulfate solution, which is the standard method. Or recovery of gold by precipitation on zinc is also a familiar example for this particular reaction. So how we are going to decide which metal to be added in the solution so that we can recover the metal already present inside that particular solution, so that we can decide with the help of the electromotive force series. So the element which is present in the on the higher position in the EMF series can displace the element which is present in the lower position in the EMF series. So it's like sodium, the sodium or lithium is the most reactive metal, so they can displace any metal present inside the solutions. However, lithium and sodium cannot be displaced by any other metal inside the particular solution. So this type of reaction, or we can say this type of process is generally known as the cementation reaction, because what we are trying to do, we are trying to recover the metallic ions present inside any solution in the form of metal powder. So, for example, copper can be displaced with the help of nickel, or copper can be displaced with the help of iron, while gold can be displaced with the help of the zinc, or cobalt can be displaced with the help of the zinc. So, these the metals uh, which we are using for the cementation process are present in the higher position in the EMF series, or we can say they are having higher electronegative potential. So uh, this is the electro this is a standard EMF series. So we can see Li is having highest electronegative potential of around minus 3.05, while fluorine is having electronegative potential of 2.87, or gold is having a electronegative potential of 1.69. So the metals which are having positive electronegative potential, that are known as cathodic, or we can say noble metals. Okay, while hydrogen is used as a reference material, then from lead to manganese, these ions are reducible from aqueous solution by virtue of over voltage, or we can say by providing some other elements having higher electronegativity inside the solution can precipitate these ions from the solutions. Then from Al to Li, which is having a electronegative potential in the range of minus 1.66 to minus 3.05, these ions cannot be reduced from aqueous solutions via any means possible. So for the recovery of these types of ions, or these types of metallic ions, we generally go with the electrolysis processes, or we have to provide extra current from the outside for the precipitation of these particular ions. Okay, so then reduction and deposition of metal via electrolytic processes. So they here we have discussed about there are some metallic ions which are having very high electronegative potential and cannot be displaced from the solution with the help of the other metallic ions. So generally for the recovery of these types of metals from the solution, we generally go with the processes of we generally go with the electrolytic processes like electrowinning or electro refining. Electrolytic process have been the workhorses of the hydrometallurgy in the recovery and purification of metal. So these are the redox reactions which are particularly imposed with the help of the external current provided. So we have to provide some extra voltage with the help of the current, so that these redox reaction can get happen inside the solutions. Or so in electrowinning, the net cell reactions are equivalent oxidation and reduction reaction, but as insoluble anodes are involved, the oxidation and reduction does not take place on equivalents of the same material. So there are two different things. One is electrowinning, one is electro refining. So as the name suggests, electrowinning. So this is the combination of two words, electron and winning. So we are trying to win the electron from the particular solution. So in this electrowinning process, generally it is like we have dissolved copper inside, and we have dissolved copper ions inside a liquid solution. So we are trying to recover that copper by applying some external voltage with the help of anode and cathode. So solution is acting as an electrolyte solution, and we are providing anode and cathode with the voltage to to complete the whole current cycle. so that current can flow from anode to cathode with the help of the electrolyte solution, so that we can recover the copper from the solution. Then there is another thing which is known as electro refining. So as the name suggests, electron plus refining. So with the help of the external current voltage, we are trying to refine the material. It's like we are taking an impure material as a cathode or anode material, while on the other hand, uh, so for example, if we are going with the cathode as an impure material, so what will happen from cathode? So the pure metal will get first, it will get dissolved inside the solution, whatever the electrolyte solution we are using for that particular reaction to get happen. So it will first get dissolved inside the solution, and then from solution it will get deposited on the anode material in its purest form. So whatever the impurities are present there, so that will get that can get dissolved inside the solution, or they can get precipitate inside the solution, depending on the voltage provided for the particular reaction to get happen. For the electrowinning of nickel from acidic nickel sulfate solution, the NiSO4 must undergo the oxidation reduction reaction. If NiSO4 is considered to ionize as Ni2 plus ions and SO4 2 positive ions, the reaction at the cathode is Ni2 positive plus 2 electron negative is going to get changed into Ni. So nickel from the solution is getting oxidized and getting deposited at the cathode material. This reaction is equivalent to that takes place in the electron refining at the anode. The oxidizing reaction is the discharge of the sulfate ion, but the sulfate radical is not stable and immediately react with water in the electrolyte to form sulfuric acid and oxygen. So this sulfuric ions are again getting reacted with the water present in the electrolyte, particular electrolyte solution, and getting converted into H2SO4 while evolving the oxygen as a gas. So coming to the gold extraction process, generally gold extraction process is done is a major example for this electro refining or electro winning processes. So in the gold extraction processes, generally we go with the cyanide leaching process. Then this leaching is performed in large aerated tanks, either mechanically or air agitated, with residence time of around 24 to 48 hours. The ore is leached at 50% pulp density with 0.01 to 0.258% cyanide inside the particular solution, and having a pH range of more than 10.5. After the cyanidation leaching, we generally go with the filtration and washing process to create a barren solid. The impurities which has not get dissolved inside this cyanide solution, while on the other hand we get a liquid solution with liquid solution consisting gold ions inside that particular liquid solution. Then we generally go with the deaeration process, and then precipitation process with the help of the zinc dust. So with the help of the zinc dust, we generally try to precipitate the gold in the powder form in metallic formation. But this gold precipitated is still having some impurities, so we generally go with the calcining or smelting processes to recover the gold bullion. The gold is made soluble by oxidizing the sulfide minerals by first is roasting, then another one is aqueous pressure oxidation process or bio-oxidation process, and thereby release free gold available to leaching by cyanidation process. So this process, this standard cyanide process is known as Merrill-Crowe process for the which is majorly used for the gold production industrially. Then there is an apart from this zinc dust precipitation process, there is another process for the gold separation from the cyanide liquid solution, that is carbon in pulp process for the separation and purification of leached gold cyanide. So carbon columns in this process, the up to the cyanidation process, the process is same. After the cyanidation process, whatever the liquid we are going to get, we provide some carbon columns for the gold to get absorbed on the particular carbon columns, and then with the help and then these carbon columns are again dissolved in some other acid, or we can say some other solvent to to recover the gold in the solution. Then from the solution we generally go with the electrowinning process for the recovery of the gold in its purest form, while the carbon left behind after the elution process can be again used back for the adsorption by carbon via carbon in pulp process. The carbon column stands in series with a bank of electrolytic cells that remove eluted gold from solution by electrodeposition on stainless steel cathodes. The solution is continuously recirculated through the elution column and the electrowinning cell. The major advantage of the CIP process is the elimination of the filtration and washing steps. So we don't need any elimination or filtration or washing step. This saves up to 50% on the capital cost and 20 to 30% in the operational cost which we were getting when we were going with the zinc precipitation processes. In CIP, the ore must be ground to finer than the carbon particles to facilitate a screen separation of the carbon from the pulp after absorption. Inorganic and organic species are also absorbed onto the carbon which are not removed by elution, and this result in a loss of gold absorption activity of carbon. So this carbon can be reactivated for some times only. After that you have to throw that. Reactivation is carried out first by acid washing to eliminate CaCO3, and then by heating the wet carbon at around 650 degrees Celsius in a rotary kiln in the absence of air to eliminate absorbed organic particles which are going to get decomposed in the uh, calcination, or we can say roasting process, in the absence of air. So in these organic compounds are getting removed from this carbon source. Then coming to the Bayer's process, which is generally used for the aluminium production from the bauxite ore. So aluminium is produced by the Bayer's process to refine bauxite ore in 5 steps to get pure alumina, which is further subjected to the whole electrolytic salt, molten salt electrolytic process in the Hall Herold salt to produce the aluminium metal from the Al2O3. So in the first step, we generally go with the Bayer's process for the recovery of pure alumina from bauxite ore, because bauxite ore is having a impurity content of around 50 to 60%. Only 40% alumina is there. However, in order to provide this Al2, in order to use this Al2O3 in the whole Herold process for the recovery of aluminium metal, we need at least a purity of around 97 to 98% Al2O3. So with the help of Bayer's process, we generally produce this 97 to 98% pure, highly pure alumina material. So in Bayer's process, first we generally go with the crushing, mixing, and desilication process. So the crushed bauxite ore is mixed with the caustic soda, which is generally known as NaOH in chemical language, caustic soda liquor, and wet grind to produce a slurry containing 35 to 40% solids, and passed down to from 200 mesh size. So prior to digestion, the slurry is heated at around 90 to 100 degrees Celsius for several hours to precipitate and remove soluble silica as DSP. So before going into the Bayer's process, we generally this as we had already talked about, this aluminum bauxite ore is having only 40%, 40 to 50% of alumina material. Rest of the things are silica and other impurity material. So silica present inside these particular bauxite ore is carrying two different forms. One is soluble silica and another one is insoluble silica. So soluble silica is also known as reactive silica, which can get reacted with acids or bases during the leaching processes. So what is going to happen when we are trying to dissolve, we are trying to create a slurry of crushed bauxite ore in the NaOH solution. So what will happen? This NaOH, the reactive silica will get reacted with this NaOH solution to prepare sodium silicate particles, or we can say it can go into the ionic form. So for removal of this silica from the solution is necessary before going for the precipitation step or before going for the digestion process with the help of the Bayer's process. So we have to remove this silica, otherwise this silica is going to create a huge problem during the digestion process of alumina. in the at temperature of around 250 to 300 degrees Celsius. So the crushed bauxite ore is mixed with the caustic soda liquor and wet grind to produce a slurry containing 35 to 40% solid and having a mass size of around 200 mass. So prior to digestion, the slurry is heated at around 90 to 100 degrees Celsius for several hours to precipitate and remove soluble silica as DSP, which is known as desilication product. So this desilication product generally consists of uh, sodium aluminosilicate. Uh, some amount of alumina is also going to get precipitate during this DSP process. So DSP causes 80 to 90% soda loss, or we can say NaOH loss is there around 80 to 90%. With less than 5% SiO2 is preferred, because less than 5% SiO2 is preferred during the Bayer's process. So 4 ton of bauxite is required to produce 2 ton of Al2O3 and 2 ton of Al2O3 to produce 1 ton of aluminium. So during the Bayer's process, first step was this crushing, mixing and desilication process. Then second step is digestion process, which is also known as the pressure leaching step. So the slurry containing bauxite is pumped into a digester, or we can say autoclave, where the aluminium bearing minerals is solubilized as sodium aluminate by reacting with a solution of hot concentrated NaOH under pressure. So this pressure and temperature conditions, whatever is required during this digestion process, it depends on the type of bauxite ore, because bauxite ore generally contains several different compounds like bohemite, dispore, and there is gibbsite. So the digestion process for these compounds varies according to their properties. So depending on the type of bauxite ore, we have to decide what temperature we are going to require and what pressure we are going to require for this pressure leaching process. Because whenever we are trying to increase the temperature, so we have to increase the pressure also at the same time, so that at this 250 or 260 degrees Celsius also the water remains in the liquid form, or we can say the NaOH solution remains in the liquid form. It does not it did not get converted into the vapor form, because vapor form will not help in the leaching process at all. So we have to increase the temperature at the same time as we are increasing the we have to increase the pressure at the same time as we are going to increase the temperature for the Bayer's process or digestion process. So the addition of 1 to 2% calcium oxide facilitates the extraction from ores containing greater than 8% bohemite and dispore. So the NaAlO2 solution containing hot slurry passes through a series of flash tanks to reduce the pressure and recover the heat lost during the process. After getting this NaAlO2 solution, we go with the clarification process. So the insoluble oxide impurities are separated from the pregnant liquor by settling or polymer flocculant or polymer flocculation process, which can accelerate the settling or thickening of the leach liquor. The solution is cooled, filtered, and a solid residue red mud consisting Fe2O3 and some unreacted Al2O3, SiO2, TiO2, Na2O sent to a long-term storage contaminant area. So this red mud, why we are calling this as red mud? Because it is containing very high amount of iron and it is red in color, and it is a huge problem for the alumina industries, aluminium production studies, because during the process, as we have already discussed, 4 ton of bauxite is required to produce 2 ton of Al2O3 material. Rest of the 2 ton is going as red mud material. So around 50 to 60% we are creating as a waste material during the Bayer's process. So many researchers many research are going on for the recovery of metals from this red mud, or how to create useful product by using this red mud, and to recover the strategic titanium material from this red mud, because this red mud sometimes contains around 8 to 10% of titanium metal, while if we compare it with the titanium ore, which is generally ilmenite or rutile sand, they contains less titanium as compared to the red mud, and they require more and more processing to for the recovery of the titanium material from rutile or ilmenite sand. Then for coming to the fourth step, after getting the least solution containing sodium aluminate, the least solution is cooled down from 100 to 75 degrees Celsius. Then it is pumped through a series of 6-story tall precipitation tanks, and solid seed crystals of alumina hydrate from the classifiers are added to the liquor to the top of each tank to nucleate aluminium trihydroxide. So we are seeding it with the help of the alumina hydrate, so we can precipitate the aluminium trihydroxide material, commonly referred to as gibbsite crystals, having a particle size of around 1 to 45 micron, and grow to larger agglomerate having size 40 greater than 45 micron as they settle in cooled supersaturated liquor. The white fluffy solid precipitate is filtered and then concentrated by evaporation, resulting in an alumina hydroxide filter cake, and the alkaline liquor is and hydrated seeds are recycled back for the leaching process and sedation process. Then this alumina hydroxide is subjected to the calcination process at around 950 to 1000 degrees Celsius to drive off any chemically bonded water, and to form and to get converted this aluminum hydroxide into gamma Al2O3, which is further required for the smelting operations via electrolytic molten salt electrolytic uh, molten salt electrolysis process during Hall Herold process for the recovery of aluminium metal. So this gamma Al2O3 contains around 0. Some impurities like 0.01 to 0.02% SiO2, then some minor amount of Fe2O3 and NaO2 is present there. Uh, while we can also go for the inert ceramic grade alumina preparation uh, via calcination to form ceramic grade alumina via calcination of this aluminum hydroxide at around 12 at temperature more than around 1250 degrees Celsius. So there are two different processes for calcination. One is at around 950 to 1000 degrees Celsius to create gamma Al2O3, which is known as smelter grade alumina, which can be subjected to the Hall Herold process for the recovery of aluminium metal. While if we are going for the calcination process at around more than 1250 degrees Celsius, so we are trying to convert this alumina, uh, trying to convert this aluminum hydroxide into alpha Al2O3, which is known as ceramic grade alumina. So this can be used as the refractory materials for furnace making and other applications. Okay, so Al2O3 is done. Now coming to electrometallurgy. So electrometallurgical processes include extraction and refining of metals by electrolysis using aqueous and fused salt electrolytes. The cathode reaction in all the processes like M Z plus Z electron equal to M, but the anode reaction will depend on the electrolyte used and on whether the process is extraction or refining. So according to that, the anode reaction will get changed. In extraction, an anode is used which does not dissolve electrolytically, such as lead alloy in copper zinc extraction from aqueous solution, or graphite or carbon in the extraction of magnesium or aluminium from a fused salt electrolyte process. The anode reaction in aqueous solution, that is also known as electrowinning process. So it will be like uh, oxidation process. So to hydroxide is getting converted into water and evolving the oxygen at the same times and leaving behind electrons in the solution. While if it is getting at the anode, if we are getting reduction reaction, so H2O is going to get converted into 4H plus plus O2 plus 4 electron negative in a fused chloride electrolyte process, in a fused oxide electrolyte. So reactions will get changed according to the need, if we are going with the electrowinning process or we are going with the electro refining process. So in refining, an impure metal is used as anode and metal ions enter the electrolytes by following the reaction of by following the reduction reaction from M, it is going to get converted into the ionic from metal is it is going to get converted into the metallic ions. So cathode reaction is getting reversed. The potential at the cathode, pure metal starting sheet or a blank or unreactive metal, is sufficient to discharge the metal ions and to dissolve the metal at the anode material. Electrorefining requires very little power to overcome E cell because the two electrodes have the same metal at similar activity. So uh, in electrometallurgy, we generally follow Nernst equation, which is E cell equal to RT divided by ZF into Ln, activity of Mz plus in cathode divided by activity of Mz plus in anode. It has to be equal to 0. So electrowinning and electrorefining are carried out in electrolytic cells made of reinforced concrete tank lined with either lead or lead alloy or PVC or high density polyethylene. So we generally go with the uh, metals which does not react with the electrolyte solutions and the acid presents or the ions presents inside that particular solution. So iron pot lined with carbon is used in generally used in the aluminum extraction process. In AL refining, the electrolyte which is basically Na3AlF6 BaCl2 having a specific gravity of around 2.8 floats on molten anode having composition of around Al then 30% copper alloy, specific gravity 4.5. Produce pure molten Al, specific gravity 2.3 at top surface as cathode. E cell is few millivolts. Then coming to the applied potential during the electrometallurgical operations, the voltage required to operate an electrolytic cell is the sum of EMF for the chemical reaction, or we can say E cell or decomposition potential, then EMF due to polarization at the anode or cathode material, and EMF to overcome the ohmic resistance of the electrolyte and the contact potential between electrodes and bus bars. So this is so some of these three is known as the applied potential, which is generally required for the production of metals by electrolysis process from their particular salts. Generally, these salts are generally metal chlorides or oxides. In molten salt requires the electrolyte has to melt at a relatively low temperature but higher than the melting point of the metal in order to collect it as a liquid. So generally when we talk about the electrolysis process, so we talked about two different conditions. One is molten salt electrolytic process and one is electrolysis process from the aqueous solution. So in either case you are going to require an electrolyte solution. Either that electrolyte solutions can be prepared with the help of the acidic solution or basic solutions by dissolving some metallic ions inside that solution to increase the conductivity of that solution, or we can go with the molten salt solutions which requires some higher temperature. Sometimes we can work with at 250 degrees Celsius or 150 degrees Celsius also, and sometimes we have to go at a temperature of around 800 or 900 degrees Celsius to get them in to get those particular metal salts into the liquid conditions so that they can act as a conductive solution or they can dissolve the metallic ions from the uh, whatever the metal we are trying to deposit at the anode or cathode material. So for example, when we talk about the gold refining, okay, so then we generally go with the refining electrolysis refining at around at room temperature itself by using some electrolytic solutions at room temperature by adding some metallic ions in an acidic solution or basic solution. Now, for example, if we are talking about the refining of Al2O3 to get them converted into the Al metal. So, in that case, we require molten salt electrolysis solution at a temperature of around 8, and we have to work at a temperature of around 800 or 900 degrees Celsius so that this particular electrolyte solution can dissolve the Al2O3, can melt the Al2O3 and dissolve that in the ionic form at that particular temperature, and then by providing the current, we can recover the aluminium in the metallic form via electrolytic deposition process. So the production of metals by electrolysis of their salts which are generally chlorides or oxides in molten salt solution, require the electrolyte has to melt at a relatively low temperature but higher than the melting point of the metal in order to collect it as a liquid. A mixture of salt is used to lower the melting point by using a composition close to the eutectic, so that we can go with as possible as lower temperature in order to save the energy during the process. The salt making up the electrolyte has to be more stable than that to be electrolyzed. So that salt has to be more stable. The decomposition voltage of the salts making up the electrolyte has to be significantly higher than that of the salt or the oxide of the metal to be deposited, so that it cannot get decomposed when we are applying the voltage for the electrolytic deposition to be happen. We then have to use alkaline or alkaline or salt which are having very high decomposition voltage, or we can say high decomposition temperatures also sometimes. Then coming to the discharge, we have talked about applied potential. Now coming to the discharge potential, the minimum potential that needs to be maintained between the electrode and electrolyte for continuous discharge of an ion is called the discharge potential. It is the sum of the reversible electrode potential and over potential, that is E discharge equal to ER plus neta. For discharge of zinc 2 positive on zinc electrode, ER equal to minus 0.76 volt and neta is around 0.2 volt. Thus, E discharge will be around 0.96 volt. The discharge potential of hydrogen is minus 1.13 volt. As for hydrogen, ER equal to EH not equal to 0 and neta equal to minus 1.13 volt. So hydrogen is generally known as a generally used as a reference potential because it is having uh, a electrode potential of 0. So if the applied voltage lies between the discharge potential of zinc and hydrogen, zinc will be deposited without hydrogen evolution if the electrode potential of a metal is more negative than minus 1.13 volt, and only hydrogen will evolve at the cathode without metal deposition. So with the help of this we can decide the particular condition, what discharge potential we have to apply it, or what applied potential we have to apply it for the deposition to get happen. Reactive base metals with more negative discharge potentials would evolve hydrogen instead of metal discharge at the cathode. Thus, calcium, sodium, magnesium, beryllium, aluminium, titanium, which are having very high electronegative potential, are electro-won or electro-refined from fused salt electrolytes process only. Deposition of Na from aqueous solution on a Hg cathode is an exception due to very high hydrogen voltage over the extremely smooth surface and very low activity of sodium in dilute solutions of mercury. So, according to discharge potentials, we can divide the all the metals present inside element periodic table into three different categories. One first category is electropositive metals that can be deposited from aqueous solutions itself by using very nominal voltage, and they are electropositive in nature because they are having electro negative voltage as in the plus. So like noble metals like gold, silver, platinum, palladium, iron, mercury, these can be deposited from aqueous solution itself by applying very nominal voltage for the deposition. While the second category is the metal, which includes the metals which can be deposited by electrolysis of aqueous solutions under hydrogen over voltage. So, according to that category, we can major example of these types of metals are lead, tin, nickel, cobalt, iron, chromium, zinc, or manganese. So we have to apply a little more voltage as compared to the noble metals for the deposition of these particular elements during the electrolytic processes. Then there are some metals which are highly electronegative, which are having very high electronegative potentials, and that can be deposited with the help of the electrolysis of fused salts only. So with the help of hydrogen over voltage, we cannot go with the deposition of these particular elements, it requires electrolysis of fused salts for the electro deposition to be happen for these particular elements. Major examples of these elements are vanadium, aluminium, beryllium, uranium, thorium, calcium, sodium, and highly electronegative lithium metals. Generally we don't go for in some cases we generally don't go for the metal making process for like lithium, sodium or potassium. We generally do not require metals of these particular elements, because uh, first, the cost of production of metal is very high due to the electrolysis of fused salts both only. And second one is they are highly reactive in nature. So even if we are able to produce the metals with very high capital or operating at very high capital or operating cost, so after producing the metals, we have to keep them in inert atmosphere so they cannot get reacted in the with the atmospheric oxygen to get them converted into converted into respective metal oxides. For examples, sodium, lithium, and potassium metals are kept inside the kerosene bar so that they cannot get react with the atmospheric oxygen to get them converted into the metal oxide. And the major problem is that the oxidation reaction of these particular elements is highly exothermic in nature, which can create blast or create um, fire during the oxidation process of these particular elements, for example lithium, sodium, and potassium. Now coming to current efficiency, the amount of metal deposited at ideal conditions according to the Faraday's law of electrolysis is M equal to ZIT. So where Z is electrochemical equivalent, or we can say gram molecular weight of the metal deposited, divided by valency into Faraday constant, while I is current supplied in ampere and T equal to time of current supply in seconds. So note Faraday constant is around 96500 coulombs per gram equivalent weight. So generally the current used exceeds the theoretically required value in depositing the metals. The current efficiency is defined as a ratio of the weight of the metal actually deposited to that which is expected to be deposited theoretically. So current efficiency can be calculated by neta equal to theoretical current requirement and what is actual current requirement which we are providing to get the deposition of that particular metal. So this anomaly neta is less than 100% is due to the unavoidable side reactions and current or metal loss which is occurring during electrolysis process, like evaporation or distillation of metal deposited, secondary reactions between the separated metal and the materials with which it comes into contact, dislodging of the deposited product from the electrode and the solubility of the metal in the electrolyte, then occurrence of side reactions of other dissolved metals, passage of current by conduction or ohmic heating, leakages to earth and between bus bars, etc. So there are several factors which affects this current efficiency. Uh, so it never comes to around 100%. So we always have to apply more current as compared to the theoretical current requirement for the proper metal deposition during the electrolytic deposition processes. So neta equal to theoretical current requirement divided by actual current requirement. It also can be defined as material actually deposited on the electrode divided by material that should have deposited theoretically with the same charge. So, like if we are, for example, the theoretical current requirement is around 5 ampere, but we have to apply 6 ampere as a actual current requirement for the proper deposition of metal. So so neta will become equal to 5 divided by 6. While on the other hand, if we talk in the terms of material, So let's say we have applied a current of 6 ampere. So we can with the help of the Faraday's with the help of this Faraday's law of electrolysis, we can calculate the theoretical amount of the material which can be deposited with the help of by using this 6 ampere current. Okay. However, in the actual conditions, whatever the theoretical amount which we are able to calculate will not be possible to get deposit in the actual conditions. So the actual amount which is getting deposited with the help of this 6 ampere current divided by the theoretical amount that should have been deposited is known as the current efficiency. So then coming to the energy efficiency, so energy is power into time. So efficiency is generally reported at the theoretical electric power applied voltage into supplied current in ampere, P equal to VI, required in comparison with actual power supplied to produce unit amount of the metal. So energy efficiencies can be calculated as theoretical cell voltage into theoretical current required divided by actual soil voltage into actual current required, or it can be defined as current efficiency into theoretical cell voltage divided by actual cell voltage. Then there are cathode area which is required for the particular metal for the 100% deposition of the metal which has to be done from the electrolyte solution. So cathode area equal to production rate divided by current density into current efficiency into electrochemical equivalent. Normally current density I equal to I upon A varies from 100 to 300 ampere per meter square, and the highest I value is used to achieve the maximum production rate. But if we are going with the highest current density, so irregular, loose and spongy deposits will be produced at very high current density. So that thing we have to keep in mind, what type of material we are trying to deposit, or what properties we are trying to achieve with that particular deposition. According to that we can define the the current density required for that particular operation. So for example, we are trying to recover 2 gram of chromium. We are trying to deposit 2 gram of chromium in 1 hour on passing 12 ampere current through a chromium electrolytic plating bath containing Cr6 plus ion. So calculate the current efficiency of the cell. Atomic weight of chromium is given. So according to Faraday's law, Z, uh, the current required according to Faraday's law, the theoretical amount of chromium which can be deposited is equal to ZIT, where Z is the mass equivalent, then I is current density, and T is time in seconds. So we are trying to deposit in 1 hour, so time will be, so Z will become 52, this molecular weight divided by the ions present, and uh, Faraday's constant equal to into 12 ampere current we are applying, and into 60 into 60. So we are converting this time of 1 hour into 3600 seconds, and the gram which we can get uh, to be deposited, that will be around 3.87 gram. Then we can calculate the current efficiency also with the help of the uh, actual amount which get deposited and the amount which we were trying to get deposit. Then it is also similar. Okay. Now coming to the magnesium extraction and decomposition potential of MgCl2. So as we had already discussed, Mg is highly electronegative in nature. So generally the production of magnesium is also done with the help of the molten salt electrolysis process. So this MgCl2, this can be recovered from various sources, like we can recover it from the ore of the we can recover this MgCl2 from dolomite ore, or we can recover this MgCl2 from the sea or saline water, sea water, with the help of the precipitation filtration and neutralization process by which is known as Dow process for the magnesium extraction from the seawater. When the cathodic and then this MgCl2 is subjected to the molten salt electrolysis process for the recovery of magnesium metals via electrode deposition in the with the help of molten salt electrolysis. The salt generally used are um, during the molten salt electrolysis is NaCl for the recovery of magnesium from this MgCl2. So when the cathodic and anodic reactions at the inert electrodes involve the cation and anion of the salt from which the metal is extracted, the reversible potential, which is known as E cell, is the decomposition potential of the salt. In the molten salt electrolysis of MgCl2 or Mg2 plus ions are discharged at the cathode to form liquid magnesium having a melting point of around 712 degrees Celsius, and chloride ions are discharged at the anode, which is graphite SCl2 gas. So the decomposition voltage for EMgCl2 is can be calculated like minus delta G naught divided by ZF. So minus 500 kilojoule divided by 2 into 96500 coulomb equal to minus 2.6 volt. So the electrolysis is carried out at by IG Fervent process and its derivatives using anhydrous MgCl2, NOx hydro process, IG Fervent process, and it starts with MgCO3, which is converted into MgCl2, and Dow process which starts with the seawater and uses MgCl2 dot 1.5 H2O. So there are different processes for electrolysis of the Mg metal from the MgCl2 or MgCO3 or MgCl2 dot 1.5 H2O, which is created with the help of the Dow process. So IG Fervent process uses an electrolyte containing 40% CaCl2, 30% NaCl, 20% KCl, and 10% MgCl2. The decomposition voltages of CaCl2, NaCl, and KCl are higher than MgCl2. So the cell design allows the removal of molten magnesium from the cathode area to prevent its contact or recombination with chloride ions. So this is the schematry of the molten salt electrolysis bath used for the recovery of the magnesium metal from MgCl2. So the Dow cell operates with partially hydrated chloride, thus avoiding a costly dehydration step. The bath composition is around 57% NaCl, 20% CaCl2, and 20% MgCl2, along with a minor part of 2% KCl and 1% calcium fluoride. The use of hydrated chloride triggers significant wear of the anode due to the formation of MgCl2 dot 2H2O plus 2 carbon changing into Mg plus 2 HCl. So highly corrosive gas HCl is getting formed um, during the process. Or apart from that, carbon oxide is also getting formed, which will result in the loss of the graphite electrode, which needs to be changed with time. The current can reach around 90,000 ampere per cell with a voltage of minus 6 volt and an energy consumption of around 18 kilowatt hour per kg mg. 0.1 kg anode is required. 0.1 kg anode per kg mg can be produced, and the current efficiency is around 80%. Now coming to the aluminum extraction and decomposition potential of Al2O3 during the Hall-Héroult process. So primary Al is extracted by electrolysis from Al2O3 dissolved in molten cryolite based fluoride electrolyte, which is generally a mixture of Na3, AlF6, AlF3, and CaF2 in the Hall-Héroult cell at a temperature of around 960 degrees Celsius. The cell reaction is like 2 by 3 Al2 is getting converted into 4 by 3 Al plus O2, and delta G naught is plus 837 kilojoule at 970 degrees Celsius. So as we can see, delta G naught is positive in nature. So according theoretically, this reaction should not get happen. But the oxygen evolved at the carbon anode reacts with carbon to form carbon dioxide, converting this like C plus O2 equal to CO2, and this delta G naught will be around minus 402 kilojoules. So the overall reaction will be like Al2O3 plus this carbon and delta G naught will be plus 435 kilojoule. and E cell or E naught cell will be around minus 1.313 volt. So carbon is effectively acting as a reducing agent, lowering the voltage necessary to supply electrical energy to dissociate the alumina. So with the help of the electrical energy supplied, this reaction can get happen. So with the help of the electrical energy supply, we are trying to get delta G naught on the negative side, so the reaction can get happen and we can recover the aluminium metal via electrode deposition. The applied voltage is around is about minus 4.4 volt to overcome polarization and resistance. The current uses up to 1 lakh ampere. So this much higher current is required during the Hall Herold process. The Hall Herold cell consists of a steel cell lined with refractory insulating bricks covered with Si3N4 bonded SiC sidewall lining. So as we can see how this much high amount of current is required for the Hall Herold processes. That's why scientists generally say the recycling of aluminium can be 95% cheaper as compared to the raw aluminium production by Hall Herold process, because the Hall Herold process required very high amount of current to utilize during the electrode deposition, molten salt electrolysis deposition of the aluminium, while recycling of aluminium can be done at very lower temperature with the help of the electric arc furnace, or we can go with the normal reverberatory or other or induction furnaces. Now coming to anodic effect, the anode effect is described as a blockade effect by an electrically insulating and non-wetting CF4 film that causes a significant increase in the cell resistance. So this inhibits the normal current flow between the anode and the electrolyte. So anode polarization voltage increases significantly and cell voltage increases very rapidly from 4.2 volt to up to 30 volt. So due to this blockage formation by CF4 film, the anodic voltage we have to increase from 4.2 volt to more than 30 volt, causing the electrolyte temperature to increase greater than 1000 degrees Celsius. As most of the current flows shift from the bottom of anodes to the side surface, large fluctuation in current flow between anodes occur, which induces instability in the aluminium metal pool. So when the alumina concentration in the electrolyte decreases less than 2%, the CO2 content decreases to around 20%, and the CO content increases to up to 65% with tetrafluoromethane making up to 10 to 20% of the total anode gas. During an anode effect, the discharge of fluorine occurs, which reacts with the anode carbon and forms CF4. So the anode effect continues until Al2O3 is added and the cell current is interrupted by an electrical salt by lowering the anodes to aluminium base or by inserting wooden poles under some of the anodes. So that thing we have to manage during the whole processing step when we are trying to recover the aluminium and the alumina concentrate in the electrolyte is getting decreased less than 2%. So this CF4 will get formed. So again when we are going to charge the fresh alumina contents inside the uh, electrolyte bath, so the cell current will be interrupted for some times and we have to provide some electrical sort, very high electrical sort uh, by lowering the anodes to Al waves or by inserting wooden poles under some of the anodes. Then coming to the improvements which has been done in the Hall Herold process in the from last 100 years. So in the 1910 we were using a current of around 20,000 ampere with a current efficiency of around 74%, and we were able to and the energy consumption for the per ton of aluminium production was very high, around 26,000 kilowatt per hour per ton of aluminium. While in the 1990s, the current requirement has gone increased up to 33 lakh ampere per cell. However, the current efficiency has gotten increased to around 95%, while reducing the energy consumption at the same time per ton of aluminum requirement from 26,000 to around 13,200. It's like 50% energy consumption has been cut down from 1910 to 1990 with the help of the improvements. Developments have taken place in the areas of lowering of production cost and greenhouse gas emission, improved insulation, pot linings, cathode and anode materials. These improvements have been obtained by increasing the size of the cell, decreasing the current density to lower thermal losses, improving the current efficiency related to better control of the magnetohydrodynamic phenomena, then using optimized bath, higher AlF3 content to minimize redissolution of Al produced and allowing lower operating temperatures. Then development of a wetted cathode coated with TiB2, TiC, zirconium carbide allows the metal to be drained away and thus avoid anode metal pad contact. So the anode cathode distance is decreased to around 2.5 centimeter, which reduces the voltage drop and energy consumption. Then coming to electrolysis of Al2O3 dissolved in AlF3 plus Kf using an inert anode at 800 degrees Celsius is tried to avoid CO or CO2 emission with higher Ws around 16 kilowatt hour per kg of aluminium. Then alternative molten salt electrowinning of aluminium. So electrolysis of AlCl3 in molten NaCl LiCl electrolytes at around 700 degrees Celsius has been developed by the Aluminium Company of America. This process, that's why this process is also known as ALCOA process for industrial Al extraction with the help of aluminium chloride. So so this thing has to be kept in mind. In the Hall Herold's process, we were using Al2O3 as a feed material, while in the ALCOA process, we are using AlCl3 as a feed material for the electrolysis of the aluminium. Alcoa's electrowinning cell utilized a bipolar multi-carbon electrode so that chlorine is evolved on the bottom surface and molten Al is deposited on the top surface of each electrode. The reversible cell voltage needed for the reduction reaction is minus 1.77 volt at 700 degrees Celsius. So, Hall Herold process is working at a temperature of around 950 degrees Celsius, while this process can be operated at a lower temperature of around 700 degrees Celsius, which can cut down the energy consumption during the process. And the cell voltage are at around 3.3 volt, while Hall Herold cell process is going on at around 4.2 voltage, with current density being 1.3 ampere per centimeter square and power consumption of 11.4 kilowatt hour per kg Al, while Hall Herold cell is taking around 13,000 kilowatt hour per kg of aluminium power consumption and 60% energy efficiency. However, the energy efficiency is lower as compared to the 95% energy efficiency of Hall Herold cell process. However, these advantages are outweighed by the cost of the extra step of chlorination of alumina. So as we have already discussed, this process required AlCl3 as a feed material. However, when we are talking about Bayer's process, so we are recovering alumina in the form of Al hydroxide. Okay, so for preparing the feed for this ALCOA process, we have to go for one more extra step after Bayer's process to get converted aluminium hydroxide into AlCl3 so that we can use this AlCl3 in this ALCOA process. So these whatever the advantage which are produced uh, with this ALCOA process are getting eliminated just by adding an extra step of chlorination of alumina and the problem of removing dioxins, making the process less attractive economically. So there is now as from other advantages, the cost gap is very high. If we are comparing advantages with the as compared to Hall Herold process, so the cost cutting is very high. So in ALCOA and Hall Herold cell process. However, when we are adding this extra step of chlorination process, so it adds to the cost of the process and it becomes less attractive economically as compared to Hall Herold cell process. So it's like if we are getting a cost cutting of only 1 or 2%, then there is no uh, advantage to going for this alcoa process, because at the same time for that 1 or 2% cost cutting we have to go with one more extra step of chlorination. So it becomes less attractive economically, as we have to provide chlorination step for aluminum hydroxide. So use of molten Na2SO4 as an alternative solvent for Al2O3 with the SOFC type anode for electrowinning of Al at 925 degrees Celsius is also reported. Okay, so this is for today. Now we will